In exactly 1.75 billion years, our planet will cross a threshold it can never return from. Every drop of liquid water on the surface will flash to steam, leaving behind a scorched, barren rock. Welcome to Channel Name. We often think of Earth as the ultimate sanctuary for life, but the reality of our sun's finite lifespan has led researchers to look beyond our own backyard, searching for worlds that might provide a far more stable foundation for civilization than what we have here. The countdown to our planet's expiration date is entirely driven by our own star. The Sun is a G-type main sequence star. It has a total lifespan of roughly 10 billion years, and it is already halfway through its fuel supply. As it burns through its internal hydrogen reserves, the nuclear fusion process continuously creates heavier elements. This alters the internal pressure, causing the Sun's outer layers to inevitably swell outward into a massive red giant. This map shows the solar system's habitable zone, the precise ring of space where temperatures allow liquid water to exist. As the Sun expands, this zone is forced outward, sweeping right past Earth's orbit. To survive that thermal shift, humanity will have to migrate. For decades, our search for a new home was incredibly narrow. We essentially looked for exact clones of Earth orbiting exact clones of our Sun. But in 2014, researchers Renee Heller and John Armstrong proposed a different approach. They calculated that Earth is actually not the biological peak for a planet. Better options exist. To find them, we have to look at the stellar classification system. Astronomers categorize stars by size and temperature using the letters O, B, A, F, G, K, and M. There is a strict rule here. As you move toward the smaller, cooler end of the spectrum, the star burns its fuel much slower, extending its lifespan drastically. At the very bottom are M-class stars, or red dwarfs. Systems like TRAPPIST-1 look appealing on paper because these tiny stars can burn consistently for trillions of years. There is a severe catch. Red dwarfs are notoriously violent. They frequently erupt with massive solar flares that strip the atmospheres right off their orbiting planets. A trillion-year lifespan is useless if the star repeatedly sterilizes its own solar system. The true biological sweet spot lies exactly in the middle, the K-Class Orange Dwarf. They offer a perfect physical balance between the volatility of our Sun and the sheer violence of a red dwarf. These orange stars are slightly cooler, holding roughly 50 to 80% of our Sun's mass. Because they are smaller, they burn their hydrogen reserves at a highly efficient rate, granting them a staggering lifespan of 30 to 40 billion years. This chart shows the timeline of habitability. A G-type star gives a planet a 10 billion year window. A K-class star gives a planet 3 to 4 times longer, providing tens of billions of extra years for biology to evolve. To maximize the benefits of an orange dwarf, a world needs to be physically larger, ideally around twice the mass of Earth. That extra mass translates directly into a stronger gravitational pull. Higher gravity allows the planet to hold on to a much thicker layer of atmospheric gases, providing better insulation and stronger protection from deep space. Below the surface, intense pressure keeps a massive planet's iron core highly molten and violently active. Trapped heat pushes outward, driving continuous plate tectonics. This geological recycling system dredges up deep-sea minerals to the surface, where a biosphere can thrive. Finally, that spinning, superheated iron core generates an incredibly dense magnetic field. This shield acts as a massive deflector against the damaging stellar winds from the host star. When you combine the multi-billion-year lifespan of an orange dwarf with the protective geological shielding of a massive rocky planet, you have the recipe for a world where biology can thrive long after the Earth has been reduced to a cinder. These worlds exist in reality. Statistically, K-class stars are twice as common as our Sun right here in the Milky Way galaxy. We are actively hunting for them. Missions like NASA's Transiting Exoplanet Survey Satellite, or TESS, were launched specifically to scan the sky for these exact stellar signatures. We have already found highly promising candidates. Kepler-62f is a prime example, a massive rocky world orbiting squarely in the habitable zone of a K-class orange dwarf. Soon, next-generation atmospheric scanning technology will let us peer into the atmospheres of planets like Kepler-62f, to detect the specific chemical markers of biology. Finding life there would prove our current home is not a permanent sanctuary. Earth is simply where our civilization started. Our eventual destination and our long-term survival may perfectly align with the warm glow of an orange sun.